All right, good morning, and welcome to the start of a new week. We have a nice collection of topics this week. I'm going to start off by talking a little bit about Java wrapper classes, and then a concept called generics, which allows one piece of code to handle different types. And then later in the week, we'll sort of put those two together and look at some built-in Java collection classes that will make our lives a lot easier as we code more complicated things. But first, um, here's a little puzzle, just to keep you entertained a little bit. Let me scoot this up just a little bit. So we'll, at the recitation, take a moment to see your answers for this. So go ahead and pause it and think about this, but just for fun, okay? And a brief discussion on the assignment. So you're working on this dynamic array 2 class. It is built off of this dynamic array class, and the idea is that you make some internal changes that makes it more efficient and work better. But I want to point out that this is really a great example of encapsulation. In other words, we have all this private internals on this thing. We have the same public interface. So in both classes, there's like the add and set and get. And it's exactly the same. And so if you wanted to basically swap out one for the other, one, you probably wouldn't call it dynamic array 2, you just rewrite dynamic array. Other code wouldn't have to change at all, right? So even though the internals of dynamic array change and how you're doubling the backing store and even what kind of things are represented as instance variables, other code would be completely seamless. And all of a sudden, it's just that their code would work faster, at least if you implement it right. So just as you're working on this, just keep that in mind, that this is an example of this sort of a little bit opaque and abstract concept of encapsulation, but it is an example of how this might work in the real world. Okay, so we are used to working with primitives, and again, the idea is that the way to think of it is that primitive variables hold values. So if you have int x equals 1, you can kind of think of that x holding that one value. And when you call a method, that value is passed to the method and assigned to a parameter. And so, for example, here is an add1 method. It takes a value in and returns 1 plus that number. This is back to being a static method, right? It's not called from an object of a class. It's just called directly. And here in main, we make a variable, we declare it and assign a value to it. That's stored in memory. And again, we've used different models here. Sometimes we just write the name and the number next to it. Sometimes we have had more complete stack and heap things with memory addresses. And with a little practice, you just kind of pick the one that works at an okay level for what you're trying to figure out here. So here we have a 1 stored in memory, and num knows where that is, right? When I call add1, what happens? Well, the value stored in here, the 1, gets assigned to number. So all of a sudden on the stack there, since this is another variable, number is created and 1 is stored there. Here, we're going to wave our hands a little bit as to the exact mechanism, but basically when you return a value, so what is number plus 1? It's 2. That value becomes available sort of for use later in the program. And in fact, in this particular case, you can kind of think of it as this call to the method. It evaluates to whatever value is returned from here. So this becomes a 2, and that's stored here in that variable. All right, so that's just, again, a little refresher on primitives, right? And the reason we need to know sort of what happens when you call a method that the value is passed is that it determines what can happen in here. Since just the value is passed, the 1 is passed here, whatever happens in here is isolated from this thing down here. And that's a good thing. You want to, again, sort of draw lines where you can understand where things change and where they don't change. All right, so again, as a sort of bit of a recap, primitive variables hold a value, and a variable has no method. You can't do a dot something on it. You can just use it in an expression. And the actual value not is passed to and returned from methods, right? So the value stored in there is passed, not the variable itself. Now for objects hold a reference to an object, and that object contains the value. So there's sort of like a level of indirection here, right? You have to kind of get used to following the chain of like reference to object. Object has inside it instance variables that hold a value. So there's sort of all this indirection going on. If you have an object and it has public methods, you can call the method from the object. So my object dot do something. And the copy of the reference, not the copy of the value, is passed to and returned from methods. And one of the things is that there's a special case where it can be null, right? So that means there's no assigned object in there. The reference is basically an empty reference. Okay, so just as a one use of why we're sort of happy with objects sometimes is like, here's a search loop with a primitive, and again we have an int array here. We have a key we are searching for. We do a for each loop looking at each element of the array one at a time. And if that value coming out of the array is equal to the key, we return the element. In other words, we're looking for a 3, we return a 3. It's sort of dumb because you could want to do true and false, but maybe it makes it a little easier to use for some reason later. So we look for 4, it returns a 4. If we don't find anything here, we're returning a -1. So there's an assumption being made here in this code that may or may not be valid. And that assumption is that -1 is not a valid value in the array. So you're hoping those are like all non-negative numbers or something like that. Otherwise, you can't tell the difference between searching for a -1 and not finding it, right? So there's an issue here, and hopefully that's both well documented in the Java docs and also well understood by people using it, that's a special value. Now, Java has a whole collection of objects called wrapper classes, and they are basically the object equivalents of primitives. So sometimes you want to be able to use an object for various reasons, and so Java has these sort of direct equivalents between these different primitives and what's called the wrapper classes. And you can tell the difference between them in some ways because the primitive types are all lowercase types, and as we've seen, most object types are all uppercase, and they're just the same, almost the same name. Boolean, capital B Boolean, byte, capital B byte. Char goes to character. Float and integer turns into integer, and that's basically it. But the main thing is these are designed to hold these kind of primitive values, but inside an object. So one question is why, and because it's a little bit of a complication. So if we want to make one of these types, it's basically the same as any other object. We need we declare the variable, and we say new. We're going to make a new object, and we give the name of the class, and then we construct it. So this 10 int primitive value is being passed into the constructor here to make a new integer type. There's actually a lot of options here, and we've sort of used some of this parse double kind of stuff, and has cropped up in some other places. But for example, the constructor is overloaded. Again, that means that there are same name but different type parameters in here. So here, if it takes a string, and it'll do its best to construct the value that's stored in there. I mean, if you pass in David, it's going to throw an exception. But if you pass in something that can be interpreted as a number, it will interpret it for you and create an actual integer value out of it. These things are immutable once they're made. In other words, you can't store a different value inside it. There's no set for the value. And the reason for that in some ways is if you make a 10, it should be a 10. You don't want to make it like call it a 10 val and then it stores 11 inside it. So the idea here is that you make it with a value and it stays that way. So you can also pull the primitive out of it. So here in the integer type, there's an int value, and you can pull out the int and use that, in some expression. Okay, so for example, let's say we had, instead of an int array search, we're doing an integer array. So again, this is going to be a collection of integer objects, and we search for an integer key. We can still loop over for each loop, pulling out the integer objects one at a time. And here we're checking, again, when we compare objects, we need to use the dot equals method to compare the values inside them as opposed to comparing their references. So equal equals only means that they're the same object, that the references are the same, whereas dot equals, if it's written correctly, means that they store the same value. So this is a common mistake to forget, because it's not illegal to check equal equals, but the meaning is different. You want to check dot equals. And so we return the object. It's an integer return type. If we find it, and if we don't find it, we can return null. So all of a sudden, there's not this like funny -1 kind of thing we have to keep track of. We can use null to say, hey, nothing was found, right? And your code can check for it. I will say, again, if you're trying to test for that, you should always check with equal, is my return value equal to null? Because this is not an object. This is an empty reference type. And so to check for null, you use equal equals. To compare two actual objects, you use dot equals. Okay? A little confusing, but you'll get used to that. Okay, so that's sort of nice in a way that all of a sudden we can use this extra null thing to indicate a special case. So what actually happens when we make, for example, an array of integer types? If you make an array of ints, of primitives, so if I make 5 ints, remember the variable is going to reference that array that is on the heap, and there's 5 spots for ints in there, and the values go in there 1, 2, 3, 4, 5, or 5, 10, 15, 20, whatever you put in there. It's a little different with an integer, a capital integer array. So you get an array of null references to integers. So again, when you make an array, it is filled with default values, and in the case of primitives, those are some sort of 0-like value. And in the case of an array of objects, that is an array of null values. And so you need to actually create those and make space to store things by looping over there and basically making new integers and storing them in the array. All right, so let's work through a little bit what's going on here. So here I'm going to go back to a little more complicated diagram for what's going on. We have a table storing all the variables we make, and the thing that the computer needs to know, the Java needs to know about, is the name of the variable, the type of it, and where it's in memory. And memory basically, again, is a collection of spots with an address. So to get to the spot, you go to location 1000. And again, these are related to, but not exactly the same as references. And we don't want to get into that right now. So this part here declares a variable, so it gets added to the table. And the question is, what gets stored in that variable, right? Well, we have to wait till we execute the right side of the assignment and figure out what gets made. So this makes a 2-element null initialized array on the heap, right? All new objects go on the heap. So again, this is not exactly really how it happens, but basically there's an area where the stack where things get added to one at a time, one on top of the next, and then the heap where things get added sort of wherever there's free space. So new integer 2 basically is saying, make me a spot for 2 integers. It's a null initialized array. In other words, they're not really integers there yet. They're just ready to hold some at some point. And this is created here at location 1008. And that is what gets stored in the vals location, right? So this reference is assigned to vals, and that's what's stored in here. So if we're using vals ever, it's going to say, okay, where's vals? Vals is in this table. It's at this location in this stack, and it says it references an array that begins here on the heap. Okay. So there's already this jump, right? It's not like the array is right here. There's a reference that says where it is. All right. Now we have code that is going to go through and assign a new integer to each one of these locations. So the first time through the loop, we are making a new integer with a 0 value, and that goes on the heap as well. And its location is what's stored or assigned to that element of the array, the 0 element of the array. So this thing is built, and the array remembers where it is here. Right? So all of a sudden I got a double jump, right? To get from, if we go to val 0, first it says, okay, where's vals? It's here. And then val 0 is this one. And it says, okay, where's my integer? It's down here. All right, so we're hopping, hopping, hopping. We loop again. We make another integer. And again, these actually don't have to be consecutive or anything. They're built one at a time, and wherever there's free space in the heap is where they get put. One can be above the other, one below, not in consecutive order or anything. It's just that I had limited space. So this gets built, and its reference gets assigned to vals 1. So 1 offset from the beginning of vals. And that's basically it, right? So, but again, it's hard to keep. The rule is when you make a variable, that goes in the table and it goes on the stack. When you make a new object, that goes on the heap, and its reference is hopefully assigned to some spot that remembers it. But then you have to track through all these spots to figure out what's really going on here. Okay? So again, this takes some practice to do, but the rules are very simple, right? Make a variable on the stack, make objects on the heap. That's really the only rule. You have to remember not to try to jump ahead of yourself and get off track. All right, so again, all this complexity is hidden from us, but we need a basic understanding to see how these objects behave when we pass them as parameters and assign them to each other and stuff like that. Assigning is really taking a reference and assigning the reference to some other object. And when we pass a parameter, again, the reference value is passed as the value to the method, and that's what is used to initialize the parameter. And then that has ramifications for how things can get modified inside the method. Now, these these capital primitive, these wrapper classes we'll see some more uses for these shortly. But why go from this nice int x equals 1 to this very complicated making of objects and stuff like that, right? So Java just decided to make it a little easier to use, and they do that through what's called autoboxing and unboxing. And that means they'll take primitives and wrap them for you and put them into these wrapper classes, and also allow you to extract out the primitives so you can use them in math expressions and so on without sort of having to do a lot of work yourself. So here I'm declaring a wrapper class integer, my int, and I'm assigning it a primitive 3. So again, there's a type mismatch here, right? One is an int and one is an integer. But again, Java, I don't really approve of this, to be honest. It's like they're very careful with types, but they allow you to switch back and forth kind of seamlessly without thinking about it. I think that's a little dangerous. But basically, when it sees code like this, my int equals 3, where this is type integer, it converts that kind of under the scenes into something that looks more like make a new integer 3 and assign that to my int. All right, so that's that's the auto boxing. It takes this primitive value and wraps it in a wrapper class. Then if I use this integer in a math expression, my int plus 3, it recognizes that, okay, this is an integer type and this is an int type. And so it decides it will extract the primitive value for you by calling my int.int value on it. So it's already a 3. 3 comes out and we add primitive 3 to it to get 6. Right? Okay, so the problem is it's so easy that you sort of start forgetting which type you're actually using, and you need to kind of concentrate and make sure you understand you're either in the object land or in primitive land, and just try to stay clear on what's going on there. Now, I've been saying all this new integer 3 stuff. Now, if you actually use that in code, let's do an example here. Okay, so integer, I'll just say x, or value, I guess, equals 3. That's going to be fine. Like I can run this code, and I'm not printing anything out. It's fine, right? In fact, this is really the easy way to do it. And so let's try to do it the long way. Integer 3. It's like, that's a new thing, right? Okay, it's like crossing it off. It says the constructor integer int is deprecated, which means it belonged to the language in the past, and it doesn't really belong to Java anymore. You can still do it, but they don't really want you to do it. Now, the quick fixes here are not really right. They just say add in this annotation saying suppress warnings. In other words, don't let Java complain that this shouldn't be done, which is not really what you want to do here. So the proper way to do it is they have the integer class, and inside the integer class there is a static method value of that takes in a primitive, and this basically returns an integer type. Okay. Now, so if I run this again, I'm not printing anything out, so like it's fine. But it's not a complaint about deprecated. Why do they do this? Well, basically, inside the integer class, they're storing some number of pre-made integer objects. And if you use one of those, they want to just give you the one that's already built for efficiency. This is like efficiency reasons. And there's some controls over that and stuff, but for the most part, just realize if you use like a small number, I think it's normally minus 127 to 128, that it's already pre-built, and so there's no like cost of allocating it on the heap. If you start using bigger numbers, it will just create that one for you, but also remember it. So if you ask for it again, it will also have it pre-built. So it's called caching. It basically stores them for later use. So again, all that is, I have trouble remembering that. I will always make a new integer 3, and then it'll complain, and I go like, oh yeah, then I go like look up how do I make a integer 3 or make, in Java, and it'll tell me to remind me this technique. But really, if I just say give me a 3, underneath it does all this correct stuff. It uses that value of and stuff like that to get an integer object out of that 3, autobox it into a wrapper class, and return it. So really, even though there's this new and this value of stuff, for the most part, you should just go ahead and use the existing shortcut, the autoboxing and unboxing. And then let me just show the unboxing. So if I print out value plus 4, again, this is a mix of types. You can't really add a big I integer and a 4 int, and it recognizes what it wants to do is pull out the value of this integer object, and it will then make that evaluate to a primitive, and then this evaluates to 7, hopefully. Okay. All right, so there are these wrapper classes, and again, we will see some more use of those shortly, but there's these shortcuts that allow you to sort of treat them like primitives. All right, now here's some code we can do. So once I make this integer a, again, it's immutable. You can't set the value that's changed. I can't, if there's a 3 stored in it, I can't change that to a 4. Once I make it, it's fixed, immutable. Okay, but I can do things that look like this. Make a equals 3, and then say a equals a plus 1. And if you look at it, it's going to then say, value equals value plus 1. Ugh. And let's just print out value. I'm going to get rid of this one here. Okay, so it prints out a 4. But I just told you that these are immutable. So what's really going on here? Well, again, you have to actually apply the rules of how this works, right? So integer a equals 3 is the same as making me an integer 3, or really using the cached one that comes from that value of method, and on the heap, and my a variable stores that reference on the stack. Okay, so a is at the beginning of the stack. What does it store? It stores a reference to the object, saying where it is. Now, what is a equals a plus 1? Well, we unbox a to be a 3 primitive. It's kind of tiny there. We then can do the math. 3 plus 1 is 4. We're going to auto box that back up into a new integer, 4. So that's going to go on the heap, right? This is creating a new, sort of under the scenes, it's creating a new integer for us. We're really using the cached one. And we assign the reference of this thing up into a. So we never changed this object here. We made a new object that's one bigger, and then made a reference that new object. Okay? Now that again is different than directly storing a value and changing the value. We are shifting around what we're actually looking at here in memory instead. So again, that's why it's important to sort of understand this variables are on the stack and they hold either a primitive or a reference value. Objects are on the heap, and when you make a new one, it creates a new one, and its value its reference is stored somewhere. Okay, so again, it's a sort of a little bit more complicated way of doing anything than it seems useful, but this will all come together when we start using these a little bit more. Okay, so that's it for this part, and then we'll continue on talking about this idea of generics.